You and I live on the Earth's crust, a thin layer of solid rock that's all around the Earth. Now, what's underneath the Earth's crust is different. It's melted rock, it's molten rock. Now, how do we know that? Because they're volcanoes. Let's say this loaf of bread is like the Earth. See? It's round like the Earth. And just like the Earth, it's got a thin, hard crust. But unlike the Earth, we can easily cut through it here in the lab. All we need is this table and this laboratory chainsaw. See, it's got a thin crust, just like the Earth. Although the crust is thin, it's thick enough to sustain life. All living things, all animals and plants, including you and me, we all live on top of the Earth's crust. So that's good. That is good. Now, how do we know that what's underneath the Earth's crust is different than what's on top? Well, you ever heard of volcanoes? So let's take a look now at the big ball Earth of science. See, it's surrounded by a thin, hard crust. And everything is on top of the crust. Even the oceans are sloshing around on top of the crust. Isn't that wild? Let's take a look at what's inside. There you go. There's the inside of the Earth. You got your core right here. That's solid iron. Then there's an outer core. That's iron and other metals. And then this part's called the mantle. It's gooey like hot tar. Then out here, that's the crust. It's thin and cool. The core, that's around 1,500 degrees Celsius. The mantle, that's around 1,200 degrees Celsius. I mean, that's way over 2,000 degrees. And then the crust, that's cool and hard as a rock. The reason we have earthquakes is because what you might think of as solid rock, the Earth's surface, is really pretty flexible. Like this big foam rubber map of science. Now, the Earth's surface is sort of floating on molten or melted rock. The surface of the Earth is floating on molten liquid rock, which is what the center of the Earth is made of. And these foam rubber plates of science in the foam rubber map of the Earth are floating on the liquid water of the pool. Not only is the Earth's surface flexible, but it's broken up into big plates. Huge, huge, huge plates we call tectonic plates. Tectonic plates. Like you can see here, that there's something called the Pacific Plate, and all around it are the continents. Now notice that not only are the continents sitting on plates, but so is the ocean. The ocean is sitting on top of something that's floating on top of molten rock. And the boundaries are always slipping and jostling on each other. Slipping, floating, jostling plates. As the plates move, they crack. And the cracks are called faults. Faults.
A fault line.
Now, because the plates are always moving a little bit, the faults can store energy, just like a spring.
A fault line.
With one plate sliding on the other. And when the energy is released, a lot of times you get an earthquake. An earthquake. Scientists measure movement of the Earth's surface with seismometers. It's from old words that mean measuring, shaking. Measuring, shaking. And here's how they work. Here's a magnet, very strong magnet. See how the paper clip sticks to it? And it's suspended on a point, so it can easily move back and forth. So watch what happens when the surface of the table moves. See, the magnet stays still, and the surface moves this way. It makes an electrical signal in this coil that shows up on this meter. This is how real seismometers work. Real ones, like this one. Now this magnet is right here, and it's hung on these springs. Now, this seismometer is set up to measure movement of the Earth's surface this way, this direction, up and down. Now, if we take the electrical signal from this seismometer and record it, then we call it a seismograph. Seismograph, writing down the shaking. And here's a seismograph right here. Watch what happens when I move my feet up and down. See, I can make the needle move. Look how much it moves. Just bending my knees, I can make the needle go wild.
Bill.
Oh, sorry. Now, back here, we have a whole bunch of seismographs. Look at them, measuring movement of the Earth's surface all over the world. Now, these are very accurate and delicate instruments, and scientists know just where they are on the Earth's surface. So by keeping track of where they are and how much they move, scientists can figure out just exactly how the Earth's surface is moving at any time. They're fabulous. So we're standing in a volcano. DZ, you're addicted to volcanoes.
Well, I am. They're one of my favorite things. I'm a geologist, and my specialty is volcanology.
Now, where are we, Dan?
Well, Bill, we're standing in the crater at Mount St. Helens, inside of what used to be the volcano before 1980. This is an explosive volcano.
It blew up. Just blew up. It's not one of those oozing hot rock, hot lava volcanoes, no. It just builds up, and then...
Mount St. Helens was erupting when some of the first pioneers and settlers came out to this area. Mount St. Helens was erupting. It erupted off and on from the year 1800 through about 1857.
So it could erupt again.
And it will. Mount St. Helens is a very young volcano. It's a very active volcano. It's building itself up and then destroying itself. And it's going to erupt again. We don't know exactly when.
Now, there's two kinds of volcanoes. Some that ooze molten rock, and others that explode. Oh, sorry. So, we're about to set off our laboratory scale model volcano of science. What we're going to do is mix some chemicals together that will cause gas to form in a liquid. This is very similar to what happens in real volcanoes. The gas bubbles forming in the liquid help drive the lava out of the cone of the volcano. It's pretty wild. See, as the lava runs down the side of the volcano, it builds up the cone, making it thick. This is what happens in real volcanoes. Now, the way we made this lava here in the lab was mixing vinegar and baking soda. They're chemicals that you can get in the grocery store, and they make carbon dioxide gas. It's the same gas you find in soft drinks. See? Pretty cool.